All right, page replacement. So what is page replacement for? When you are starting a process, you somehow have to save this process in the memory of your computer. But to do that efficiently, the process is divided into multiple smaller parts, which are the pages, and the memory is also divided into smaller parts, which are the frames. You can remember that you put a picture into a frame, and in this case you put your pages into the frame, so you can somehow remember which one is which. So the frame is the hardware in the memory, and the pages are the snippets of the process you are executing. It is important that the pages are the same size as the frames, so when your process is divided into number X of pages, it will also fill out number X of frames. So now the thing is, you might have a process that is so big that you end up having more pages than you have frames in your memory. Right, so here we have 12 pages, but we only have 9 frames, which are of course fictional and very, very low numbers. In reality, they would be much higher. So what we have to do is we can always only load a fraction of the process into the memory. And when we need a different part of the process that is not in the memory yet, we have to take a part of the memory out and write it to the disk. Beautiful. So that we can load a new page into that frame. But we have to decide what page we load. And for that, there are different page replacement algorithms. Maybe to make this scenario a little bit more clear, if it is hard to understand, imagine you are drawing a picture and you have, I don't know, let's say 20 colors. Beautiful. So you have 20 pencils with different colors lying around, and you have some kind of a quick access where you can store 3 pencils so that you can grab them really fast and you can change colors very quickly without searching for pencils here in your whole collection. But your picture needs more than 3 colors. So let's imagine you're painting with these 3 colors, but then you need a color that is here in your whole collection and you don't have in your quick access. So you have to put one pencil out of your quick access and put this pencil into your quick access before you can draw with it. But this process of changing the colors, putting one out of the quick access and putting one back in, is a very long process. So you don't want to do that too often. And then you have to decide which of the 3 colors you have here you will put out. Now, in the perfect world, you would say, okay, I will put that one out that I will need latest in the future. So if I need these 2 pencils before this one, I will put this one out. The problem is that you don't know which pencil you will need next, so that is not really an option. But what you could do, for example, is putting that pencil out that you had in for the longest time, or you could put that out that you haven't used for the longest time. So these would be different replacement algorithms, and that is what you also use for page replacement. So you could, for example, say, if I want to load a new page into my memory, I put a page out of the memory that has been there for the longest time. That would be first in, first out, or the FIFO algorithm. Let me write that down. First in, first out, FIFO. Or you could say, I replace the page that I haven't used for the longest time. No matter how, if another frame or page is in the memory for more time, I replace that one that I haven't used for the longest time, because there I have a higher chance that I won't use it in the near future as well. So that would be the least recently used algorithm. Least recently used. So let's get to a practical example. Let's say we have a reference string, which would be the numbers of the pages that we load or that we need to process, that we need to access in the memory in a specific order. So let's take, for example, the reference string 1, 2, 3, 7, 1. So these are our pages that we need to access in memory, that we need to run the current program. But as I said, with a picture where we don't know which color we will need next, here we also don't know which page we need next, and therefore we can't look into the future. And this is what keeps us from using another algorithm that I forgot earlier, which would be the optimal page replacement algorithm. I said that because usually you can't use that. But that would be the optimal case. If I could see, okay, I'm at this point and now I have to load the 7. Okay, which one of the pages I loaded earlier I won't use in the near future, or which will take the longest until I will use it again. That doesn't work. So this is our reference string. Then you have your frames in the memory, starting with, in this case, F1, let's say, 2, 3, yeah, and let's do 4 memory spaces. So, okay. Here we have 1 line left, but we will come to that very soon. Let's first load the process or the pages to memory to the frames we have in the order they appear. So first we load page 1, then we still, in the second frame, we still have, or in the second let's say time point, we still have 1, but then we add 2. We have 1, 2, and add 3. Here we have 1, 2, 3, and add 4. And every time we try to access something from our memory that is not there yet, and we have to load it into memory, that is a page fault. So a page fault just means you want to access something in memory that's not there yet, and you have to load it. So here we have to load 1, we have to load 2, 3, 4, and every time we have a page fault. And you want to keep the number of page faults as low as possible, because every time you have a page fault, that basically means that you have to put a pencil from your collection to your quick access before you can use it, which is a very slow process, because in reality that involves loading a page from the disk to the memory, and your storage device is much slower than your memory, and therefore whenever you have to load something from the disk to memory, that takes a lot of time. So you want to avoid that, and that's basically what these algorithms are for, to keep the number of page faults as low as possible. So here in the first few steps you can't do much, because you just have to load, like your memory is empty, so you have to load everything that you want to access to memory first. That will always be the same. So here we have 1 page fault, 2, 3, 4, and now here comes the part where we have to decide which page do we actually replace? Because we want to load the 5 and we have to take something out. And that actually differs depending on which algorithm you use. So let's start with the simplest one. Let's start with FIFO, first in, first out. As 1 is in the memory for the longest time, we will replace that and instead put a 5 there. Then the rest stays the same, 2, 3, 4, and because we had to load something to memory, we have another page fault and count, so we had 5 page faults so far. Now we have the 7. It isn't in here yet, so we have to replace something. Now after the 1, the thing that was in the longest is the 2, so we replace that. So we have 5, 7, 3, 4. Then we want to load the 6, we do the same again. Now the 3 is the one that has been the longest in memory, so we replace that. And then here we have a 7. Oh, and of course we count our page faults. And now here we have the 7, but the 7 is already in memory, so we have to do nothing. We can access it right away without loading it to memory. So our table doesn't change, or at least this row of the table doesn't change. And we also don't count a page fault, so we still have 7 page faults. Now 8 is not in there, and now we have to see which one of the pages is in here for the longest. Now that we already replaced these 3, 4 is in for the longest. So we replace that one. 5, 7, 6, and now 8. We had to load something to memory, so we count that page fault. 2 isn't in here as well, and now 5 is the one that has been in here the longest. And you might already see a pattern. If you do it in a table graphically like here, you can actually always go to the next line down if you have to do a replacement. So you will replace this one, then this one, this one, this one, and then you will start at the top again, as long as you have to replace one page. So now we need the 3 that is not in here. We had the 2 last time, so now it is the 7 that we replace. And another page fault. 3 is already in here, so nothing changes. The number of page faults stays the same. 2 is also already in here, nothing changes. Still 10 page faults. And 5 we deleted earlier or replaced earlier. So now we have to write it back here and see where we can put it. So 2 has been in for 4 cycles, 3 for 3, 6 has been in here the longest. When we look, 8 came in here, we have to replace the 6. And then next time as we go from top to bottom, it will be 8. Now we need the 4, not in here, so now we replace the 8 with the 4. Oh, and of course, don't forget to count the page faults. 7 isn't in here as well. Now 2 is the one that has been in here the longest since this point. Then here we had 3, 5, 4, so we replace the 2. 4, 13, and we don't have 1. Now we replace the 3. And we end up with 14 page faults. So that is basically the FIFO algorithm, or the first in, first out, which is not too hard to do. But we can use the number of page faults to compare it to other algorithms and see if another algorithm would perform faster. And that's what we're gonna do next. Okay, let's start this again because the storage, not only the memory, but the storage of my phone was full. So let's continue with the next algorithm, which is the least recently used. By the way, I'm not sponsored by the EWE, but on the other hand, I got this paper for free, so in some way I might be sponsored by them. Okay, so yeah, least recently used. I'm only going to write LRU to save some space here. And we basically start doing the same again. We make the table with our reference string. And we use the same one again, so we have comparable results. So we have 1, 2, 3, 4, 5. I'm going to save you the time. So we start in the same way, but before, remember here we just replaced the page that has been in memory for the longest time. This process will be a little bit more complicated, and therefore we will make some kind of a queue. Yeah, to keep track of the order in which we loaded the processes. You don't need to do that, but it makes it much easier, and I think especially for this explanation it might make things more clear. So we start loading the first page again, then we keep that one, load the second, and we do that until our memory is full. So far, as I explained earlier, no difference. You load 1, 2, 3, 4 because there's nothing to replace. But now we have the 5th page, but only 4 frames, so we have to replace something, and we have to decide what we replace. Instead of replacing the one that has been in for the longest, we replace the one that we haven't been using for the longest time, which in this case would be the same because we used everything only once. So the one that we used first is also the one that we used the longest time ago. So we will replace the page 1. Oh, and of course we have to count our page faults. So 1, 2, 3, 4, 5. And also we have to write a queue. I should have done that from the beginning on. I'm sorry for that inconsistency, but it is still early enough. So in our queue, we see what we loaded to memory. So we had 1, 2, 3, 4, and now 5, and 1 is out. So now we load 7, and again, the one that we loaded second is also the one that we haven't used for the second longest time after 1, which we already replaced. So now we are going to replace this one with the 7, and the rest stays the same. So up until here, there's no difference. It's exactly the same, and it will be exactly the same again because we still used everything only once, and now we have to load something new. So we will load the 6 here because we haven't used the 3 for the longest time from everything which is still in here. 7 page faults. We note down the inconsistency again, the 7 and the 6 here again. 2 is out, 3 is out. And now it becomes interesting because now we want to load the 7 again. We have 7 still in here, so in the memory basically nothing changes. Also the number of the page faults doesn't change, but what changes is in which order we accessed the pages last. So now, even though we didn't replace it or load it into memory, 7 is the one that we accessed last. Even though it is in the memory longer than the 6, for example, we accessed it after the 6. And that's what we need this queue for. Here it comes in handy because now we can take away this 7 and put it at the end of the list again. And it being at the end of the list, we see that we used it last. So now we want to load 8. And 7 is definitely no option. Here we can see in our list the one that has been in the longest is the 4. So we replace that. And from this point on, the list really makes sense. Before we could just replace like in the FIFO very easily, but now it makes sense to have this list. So we replace the 4 with the 8, count a page fault, and we take away the 4 here and put the 8 in the end. showing that this is the one we accessed last. Now we want to load the 2, and we can see in our list that 5 is the one that we haven't used for the longest time. So we replace that one. The rest stays the same, but as we loaded something to memory, we count a page fault, and here we cross out the 5 and put the 2 at the end of the list. Then we want to load 3. We can see 6 is the one that was least recently used, so we replace that. 6 right with the 3, the 8 stays, 10 page faults, and we always have to remember to take away the number we replace and put the new number, in this case 3, at the end of the list. Then here is a special scenario because we have 3 again, so it stays everything as it is. But 3 is already at the end of the list, so even here nothing changes. But just for the sake of completeness and to make it clear, we will do the same process again. We take away the 3 and put it at the end of the list. Doesn't change anything, but I think it becomes more clear if we do it this way. Okay, then the same with the 2. We still have 2 in memory. Nothing changes here. No page fault, but 2 is not at the end of the list. So here it actually makes sense to take it away here and put it at the end of the list. Now we want to load 5. This is not in the memory, so we have to replace something, and that will be 7, as we can see here. So 2, 5, 3, 8, and we have a page fault. Take away the 7, put the 5 at the end, and then we continue with 4. Last recently used is 8, so we replace that. This all stays the same, and we put the 4 here, 12 page faults, and we make our change down here. 7, not in the list. Least recently used is the 3, so that will be replaced. Another page fault here, updating our list or our queue. And now we have the 1. It's not in the list. What do we replace? The 2. 1, 5, 7, 4. Now for completeness, we can take away the 2 and put the 1 at the end, but now it doesn't matter anymore because we are finished. And again, we have 14 page faults. So if we are comparing the 2 algorithms in this case, we see that there's, in this case at least, no difference. We have 14 page faults for FIFO and 14 page faults for LRU. But that is a rather unusual case. Generally, the LRU is the more efficient one. So when you have a much longer reference string, chances are that you will have less page faults with this algorithm than with the FIFO. But the smaller the reference string is, the higher is the probability that you have a scenario that is atypical. But in a realistic scenario, first of all, you would have many more pages than 4 frames, I mean, pages as well. And the reference string would be much longer. So you will, in practicality, probably never run into a scenario like here. But if you would have this in an exam, you could argue, okay, in this specific case, it doesn't matter if you use FIFO or LRU. But in a practical scenario, LRU would, in most cases, be the more efficient one. Oh, and one thing additionally, here I'm counting from frame 1 to 4 from top to bottom. It might be that when you are giving a table or when you see how other people do that they start from the other direction. So frame 1 will be the lowest and then they go up to frame 4 or they start with frame 0 counting. But for the algorithm, that absolutely doesn't make a difference. It could only happen that in the end you don't have the memory state of 1574, but that you have 4754. 1. But this is just mirrored. So everything that happens in here at the latest state is exactly the same. Theoretically, even though it doesn't make a lot of sense, you could also do F2, F1, F4, F3 or whatever, because the process is still exactly the same. Of course, this wouldn't make sense. Don't do that. But just to make it clear, if you do it from top to bottom or bottom to top or whichever order, doesn't matter. The process, the algorithm is still exactly the same. Okay, I hope I could make that topic clear. And if there are any questions, let me know.